All right, so welcome back. Today in this video, we're going to be continuing our water resources and environmental engineering section of the review. And today we're going to be specifically looking at basic hydraulics. If you missed the previous video on basic hydrology, went over rainfall, intensity, runoff, infiltration, all of those things. Make sure that you check out that video as well. It goes over and highlights some stuff that they're definitely going to ask you on the exam. All right, so take a look at number one. Number one says calculate the velocity of water in a rectangular open channel with a Manning's roughness coefficient of 0.03, a channel slope of 0.001, and a hydraulic radius of 2 meters. All right, so what information do they give us, right? All right, so given information is we have a roughness coefficient, We also have the channel slope, right, which is 0.001, so channel slope. And we have the hydraulic radius. Okay, what are we trying to find? We're trying to calculate the velocity of water. So we're trying to find the velocity of water. All right, formulas needed. Well, I know they give us something that's really that could be really crucial. So we know that it's in an open rectangular open channel, and it has Manning's roughness coefficient. So we need to look up Manning. Because I don't know what Manning's. Manning's equation. All right. Q, what is Q? Discharge or flow. So I'm not really solving for flow, looking for velocity. All right, let's look at the next equation. V, what is V? Velocity. Okay. What is K? K looks to be like a constant and a known value. So if we're using USCS, which would be like feet, we would be using 1.486, but we're using SI unit, so I know K is 1. Okay. Do we have RH? The hydraulic radius. We have that, 2 meters. Okay. And do we have S? S is slope. We have the channel slope. All right, so we have everything we need. So the formula would be V is equal to K over N. What's N? The roughness coefficient, which we do have that as well. Okay. All right. So K over N, all right. R sub H to the 2/3, and then times S to the 1/2 power. Don't forget those 2/3 and 1/2 powers. They're very important. And it can mess up your equation if you don't plug in everything correctly. Okay, so let's go ahead and write out what we know. So V is equal to question mark. We don't know that. K in this case is equal to 1 because we're in SI units. N is equal to 0.03. R sub H, put some commas between these. R sub H is our hydraulic radius, which equals 2 meters. And S is the slope of the channel, which is equal to 0.001. All right, when we plug in our values, we get V is equal to 1 over 0.03 times 2 to the 2 over 3, right, times 0.001 all to the 1/2 power. All right. And when I solve everything out, I get 1.67 meters per second, or A. All right, let's look at number 2. Number 2 says a fluid. Now zoom in a little bit more, so hopefully you can see a little bit better. Fluid is flowing in a horizontal pipe. One section, the fluid has a pressure of P1 is equal to 150 kilopascals. A velocity of V1 is equal to 10 meters per second, and a density of 1,000 kilograms per meter cubed. At another section, the pressure is for P2 is equal to 100 kilopascals, and the velocity is for this particular section 5 meters per second. If we neglect the effect of gravitational potential energy, what is the difference in elevation between the two sections? Okay, so where do we start? So first we want to start by labeling out what the information that we're given. We are given velocity of the fluid flowing through a horizontal pipe. Velocity, so we're given velocity, we're given pressure, and we're also given the density of fluid. And it's important to note all of these are given at 2 points in this horizontal pipe, right? All right, we are trying to find the change in elevation. Okay, so how do we start this problem? Well, we need to definitely get to an area where we're looking at fluid flow. Fluids flowing through a pipe. All right, so there's a lot of ways, or a few different ways you can go about this, but if you have some prior knowledge, let's just do fluid flow. See if anything comes up. It's like the index. Wait, let's go back. All right. So principles of one-dimensional fluid flow. Okay. So energy equation. Steady with no energy input. Okay, this deals with head loss, so no. Bernoulli's equation derived when energy, assuming no friction loss, that no pump or turbine exists between sections 1 and 2 of the system. Okay, so there's different sections in this particular system, and that's what Bernoulli's equation goes through. So we get P2. So we have P2, We have, so that's the section part 2. We also have the velocity of part 2. Do we have this value? What is that value? That's the fluid density. So the fluid density is 1,000 kilograms per meter cubed. So we do have that information. Do we have gravity? We should, yeah. I mean, gravity is 9.8 meters per second squared. What else do we have? We have P1. So we don't have Z2, which is our elevation at the second section. So key to note, we have P1, we have density, and we have V1 as well. So the only values we're missing is Z2 and Z1. So we know that we can find the difference in those just by isolating them and having it say Z2 minus Z1, right? So I kind of walk myself through the problem to make sure I have all my variables that I need before I start solving. As you go through this process, you won't waste a ton of time because you'll kind of go through what you're given and what you're trying to find. And I know I'm trying to find a change in elevation. So, all right, let's start writing this out. So I know that the formula that I need is going to be P2 over the density plus the second velocity of the section squared over 2. And I'm just copying this. Plus Z2 times G is equal to P1 for P plus V1 squared over 2 plus Z1 times G. Okay, so I'm just going to list out all of these variables so that you're not confused. Okay, so what is P2? P2 is equal to 100 kPa. What's the density? 1,000 kilograms per meter cubed. So that is density, that is not P. I know those symbols, I'm writing them very, very similar. What's V2? Equal to 5 meters per second. What is Z2? That's equal to, we don't know. What is G? 9.81 meters per second squared. What is, and I'm just going down the line of the equation, right? What is P1? P1 is equal to 150 kPa. All right. And then density is again 1,000 kilograms per meter cubed. V1 is equal to 10 meters per second. And then Z1, we do not know again. And G is 9.8 meters per second squared. All right, so let's plug and chug. Switch colors. Red is not what I want to see anymore. All right, so let's plug and chug for this. So we get 100 kPa over 1,000 kilograms per meter cubed plus 5 meters per second. Square that all over 2 plus Z2 times 9.81 meters per second squared. Okay. What else? That's all equal to 150 kPa over 1,000 kilograms per meter cubed plus 10 meters per second. All that is squared divided by 2 plus Z1. I'm running out of room. Start erasing. Hopefully you wrote those values down. So Z1 times my 9.81 meters per second squared. All right, so we got Z2 and Z1 that we don't know. So we just want to get everything a little bit more simplified. And it should simplify down to 9.81 times Z2 minus Z1 is equal to 0.05 plus 37.5. And so the distance or the difference in elevation, Z2 minus Z1, which is what we're solving for, is equal to 3.82 meters. Okay. All right, so it's a bit of just listing out everything, knowing which equation to use. Bernoulli is a big one. Manning's equation is another big one. So if they're giving you pressures, velocities, fluid flow, fluid going through a pipe, Bernoulli is probably going to be your go-to. All right, let's look at number 3. This one says the Bernoulli equation states that the sum of the pressure, velocity, and elevation head is what? Okay. So what information are we given? Well, we're looking at the Bernoulli equation. Find what it states. What does it state? Right. Okay. So the field is derived. So I'm just looking in the handbook. I feel like okay. So I started just looking for the Bernoulli equation, and I figured I was in the right area because of this. I scrolled down just a little bit further and see that the Bernoulli equation states that the sum of the pressure, velocity, and elevation head is constant. So is constant. So A. All right, so this concludes this section. I think it's the hydrology. Or no, this is basic hydraulics. The other one was basic hydrology, but yeah, this concludes the basic hydraulics section of the water and environmental engineering review. In the next section, we're going to be looking at pumps. Have a few practice problems for you on that. So I'll see you in the next one.